Welcome back. In this video, we will take a look at a special kind of path and a special kind of circuit. It's called an Euler. I know it looks like Euler, but it's an Euler path or an Euler circuit. Now, we're going to begin this topic by looking at a little game here. Okay, this game says trace each drawing. There's drawings below, right? Trace each drawing without lifting your pencil or pen and without retracing any of the edges. Okay, wait a second. What do I mean? Well, when I say trace the drawing, that means, make the complete picture, right? Complete picture. So you have to draw the entire thing. Okay, so let's try the one on the far left. Well, the question that is hopefully going to be answered a little bit in this unit is, where would I start? Well, since we don't have maybe any idea, we'll just pick a spot. I'll just start at the very bottom. I'll start down here, okay? My goal is to start there without lifting my pen or pencil and without retracing any edge, basically draw the entire drawing. Well, if I go up to the right and then over to the left, and then I say, oh, I'm going to come back down, I get stuck because I basically have already came back to where I started, but there's no way to go away from there without retracing my steps. I'm like, okay, that didn't work. Let's try it differently. Maybe let's go up over here, and then maybe I'll go over here, and then over here and over here. Remember, I can go back to the same vertex. I just can't retrace the edge. So good so far. Then I'll go down here, then I'll go up here, then I'll go down, then I'll go over, and then I'll go down. I did it. Yay, I won the game, right? I traced every single edge without lifting my pen or pencil, and I did not retrace any edge. Now, the next one to the middle actually looks less complex, but it turns out it's a little more complex. If you pick any random spot, as I did, like the bottom or whatever, it may or may not work. So, for example, if you start at the top and you try to retrace this without picking up your pencil, what you'll find, and I'm doing it here, you see me do it live, is that, I kind of get stuck, right? I'm back to where I started, but I have not retraced every edge. What you'll find is that if you pick certain spots, you won't be able to do it. This graph, and we'll learn later why, only has two spots, the bottom left and the bottom right, where you can start to trace this. And even if you start at those, it doesn't necessarily guarantee you'll do it correctly. I'll try it right now. Let's see if I can get it right. I don't know that I can. I'm going to start from the bottom left. I'm going to go up diagonally and then over, and then I'm going to catch the top, and I'm going to come down, and I'm going to go over here, down, and across. It looks like I did it successfully. It can be done. By the way, that was a path. I don't know if you noticed that, but this one was a circuit. Now, why was that the case? On the first one, I started and stopped at the bottom, right? This is my start and my end. But on the second game, I actually started over here, kind of interesting, but I ended over here to the right. You could always replay the video to catch that for yourself. Well, on this last one, it's actually not possible, and I'm not going to play it out. But it turns out if you try this one as many times as you want, and you can try this a bunch of times by pausing the video, you'll never be able to actually win this game. Not possible to win. And so we're going to take a look at some reasons why in just a second. But first, let's introduce some new ideas. All right. So we're going to talk about something here called the degree of a vertex. So the degree of a vertex is the number of edges meeting at the vertex. So it is possible to have degree 0, although that doesn't mean much as a map. But if you just have one edge connecting, right, that's going to be degree 1. If you have 2 edges connecting to a vertex, degree 2, degree 3 with 3 edges, and so on, you could have degree 4, you could have degree 5, 6, as many times as you have an edge connecting to a vertex. All right. So here's a couple theorems that will help us play that game from before, and it has to do with something called an Euler path or an Euler circuit. And I haven't yet defined what that is, so let me take a moment to do that. All right. So an Euler path, what would that be? It is a path through all. Well, obviously it's a path through all edges without repeat. All right. And there's something called an Euler circuit. We've already talked about what a circuit is in a previous video where you start and end at the same place, but it's going to be circuit through all edges, okay, without repeating the edges. And of course, that is because, remember, circuits are path. The key on both of these, really the key on both of these, is all edges, all edges. So that's like the game we played above. Okay, you can't just start and stop at one particular place. You have to go through all of the edges. And there might be some reasons why we want to study these, and we'll see this later. So now we're going to get a couple of theorems that Euler found out. All right, these are about Euler paths and circuits. Theorem number one says a graph will contain an Euler path if it contains at most two vertices of odd degree. At most two, that just another way of saying two or less, right? 2 or 0. And you might be thinking, well, like 2, 1, or 0, but you actually can never have one, but we're not going to discuss that in detail now. And let's take a look at what I mean by that. So let's take a look at these pictures down here below. And by the way, we're going to come back and look at that second theorem in a second. All right, let's take a look at this middle picture. You might remember this middle one. I did this at the start of this video, and we found a path, right, that started at D. Remember, it started here at D, and I ended up at C. I was able to do that. And so let's see what it has to do with this thing called the degree. All right, so if you look at starting at E at the top, notice there's two edges connected to E, so that's degree 2. I'm just going to put a little 2 there. A has 1, 2, 3, 4 edges connected to it. That's degree 4. By the way, those are both even numbers. Remember, our theorem has something to do with odd degree. B also has 4, all right? But D and C are different. D has degree 3, and C has degree 3. Now, this theorem says a graph will contain an Euler path, meaning you can go through all of the edges once, if it contains at most 2 vertices of odd degree. And we have exactly 2, right? We have 3 and 3. Those are both odd numbers. And it's no surprise, actually, that you have to start and end at the odds, because otherwise you would go away from them. So we can also start at the other odd. Let's see if I can do this differently. I'm going to try and trace this. Let me get my highlighter. 1, 2, 3, 4, 5, 6. There we go. That time I started at C and ended at D. Let's take a look at the second theorem. A graph will contain an Euler circuit if all vertices have even degree, so no odds at all. Now remember that I was able to find a circuit that went through all of the edges, in other words, playing that little game at the start. And if you take a look at this graph, you can see that they're all even. E has degree 2, A is 4, B is 4, D is 4, C is 4, and F is 2. All of those are even numbers. However, the reason that I could not remember, it was not possible on this one, in this case, to find, and let me give it the name, Euler path or Euler circuit, because it did not satisfy either of the theorems above. If you take a look at the dots that are already in red, A has degree 1, 2, 3, 4, 5. That's an odd number. And actually B has 5, C has 5, and D has 5. That's 4 different odd numbers. Well, it certainly won't have an Euler circuit because they have to all be even, right? And those are 4 odds. But in the first theorem, it says it will only have an Euler path if it has at most 2 of odd degree, 2 or less. In this case, it has 4. That's why it's not possible, all right? We can use these theorems if we look at a variety of maps and decide if they have Euler paths or Euler circuits. Now, remember this original Konigsberg bridge problem, which was, can we cross all 7 bridges? In this case, they look like edges, right? Can we cross all 7 bridges once, without repeating the edges? Now, this does not say a circuit. It doesn't say we have to start and end. All we're basically going to look for here is an Euler path. Does it exist? Well, one way to do it is just play with it forever and see if you can start somewhere and go through all of the edges without repeat, and you'll get pretty frustrated after a while. Like if you start at D, you might go up here, you might go down here, you might come over here, up here, and then up here, and then like, oh wow, I'm stuck. I didn't cover all the edges. In other words, you can play this game for a long time by trying it, but with these theorems, you have more power just by looking at the degree. Notice that D on the far right has 1, 2, 3, has degree 3. L has degree 3. That's already 2 odds. R has degree 3. That's 3 odds. And A actually has degree 5. That's 4 different odds. So is there an Euler path? No, it's not possible because we have more than 2 odd degrees. All right. We have actually 4 of them. So it is not possible. You cannot find an Euler path. Okay, we're going to take a look at some problems that you can decide whether there's an Euler path or an Euler circuit and practice those to complete this. Okay, now that you've looked at those, I hope that you understand a little bit more about what determines an Euler path or an Euler circuit.